This video is about cartography and symbolizing data and data types. So the purpose of a map is to show relationships between spatial data. Spatial data is data that has location attached to it, so place is very important in spatial data. And so the best way to show spatial data is using a map. Data that's not spatial doesn't need to be shown with a map, really can't be shown with a map, because data that's not spatial doesn't have location attached to it, it can't be mapped. Maybe if you're creative you could. So cartography is the art and science of map making, which is the art and science of displaying spatial data. The whole point is to display spatial data. We want to make this information easily interpreted, easily understood by our map viewer. So the person reading the map wants to understand it. It's your job as a cartographer to make that happen. Cartography is an art because it involves decision making, personal choices, personal bias, design. There are some people that have like a natural eye for design and make things look good. And there are some people who don't and maybe have to try a little bit harder at design. I'm like not a great designer. Like in my home, I just hang stuff up and build things. My wife tells me where to put it and what it should look like. But cartography, I'm okay at that design element. It's definitely not my specialty, and there are people who are both naturally and who have tried very hard to become good at the design element in cartography. We have a whole class on cartographic methods in our certificate. That's Geography 114. So this example here, it's from my spatial analysis class, Geog 12, the one after this in the series. Students are given a data set of restaurants in Pasadena around PCC. Their task is to geo-reference those cities, and so they have to turn an address table into point data. So they have spatial information. They have to turn that spatial information into map layers. What I don't tell them how to do is how to display the data, so at that point they're good enough where they can make those design choices for themselves. The one above, I think maybe doesn't look as good as the one below, but it does have some different information. It tells you quarter mile, 1 mile, and just general area restaurants, and so you have a distance metric. The one below, probably just the base map here makes this map look better than that one, where the beige background doesn't look great. But the one below has restaurant names. It does not tell you distance. They zoomed in and they're only showing the restaurants within a quarter mile. So, and other design things, that scale bar is kind of too big. It doesn't need to be that big. I like the size of this one better. But between the two maps, same data set. Students found ways to show different things, how to make the maps good for different purposes, using that same set of information. And that's based purely on cartography. It's based purely on their design choices. Cartography is a science because it uses data, that spatial data I've been talking about. That data has to be collected somehow. Hopefully it's collected with a scientific method. Hopefully it's an accurate representation of real life. Hopefully it's good data. You want to be careful of your data sources when you're pulling information in from other places. But that makes it the science. The whole point is you have spatial information. You're trying to convey that. You're trying to communicate it. In some science agencies, one of the positions that they have is like a data visualizer or data communicator. And we've had PCC students work for NASA, JPL, as the data visualization person. And really that means make maps and make complicated things look good and easily to understand. Now, with all that data, symbolizing it is the process of applying colors and symbols to information so that people can understand what it is. And so when you're putting data onto a map, you have to apply colors or symbols to make it appear. The best way to do your symbolization or symbology really depends on the data type. Certain types of data are best symbolized in certain ways. Qualitative data is data that is qualities, kinds, or types of things. Qualitative data can be a description. In other academic fields, interviews might be qualitative data, descriptions might be qualitative data. A lot of like living person anthropology is qualitative data. Case studies are qualitative. In GIS, we kind of distill qualitative data, all that stuff, into two groups. Nominal, which is names or identities. These could be numbers if the number is arbitrary, like a census block or a zip code or a parcel number. It's proper names, animal names. It could be descriptions, like your nominal data could just be a description of it. But these are things, countries, states, plant type, animal type, that's all nominal. Categorical data is groups or classes of data. Still qualitative, and it's important that those groups are not ranked. So road type is an example, vegetation type, geologic coverage or land unit is categorical, land use. Now, I would accept the argument that all those things I listed could be considered quantitative, the other one, where road type, you could quantify that based on speed, capacity, the size of the road. Freeway is clearly bigger than a surface street. But road type is not necessarily quantitative. Vegetation type as well. Vegetation density, sure, quantitative. But is Mediterranean chaparral coverage better or worse or more or less than cactus sage scrub? Is rainforest, different rainforest category, whatever. So veg type, you could find ways to make that quantitative, but it's, as described here, that's going to be qualitative. Same with land use, agricultural land, urban areas, private land, park land. That's qualitative, that's groups. Geology, igneous extrusive is going to be a group. Igneous intrusive is going to be a group. Sedimentary, all your different sedimentary types, metamorphic, and so on. Now, if your geology map is showing maybe age of the rock or time period of when it was deposited, maybe that's quantitative. But rock type, categorical, qualitative. This baseball map here is one example of representative colors to show quantitative data. Representative colors are when a color automatically, kind of in your brain, matches up with the color of a thing in real life. On this baseball map, most of the teams are using representative colors, where the Dodgers are Dodger blue, the Padres are kind of their blue-purple, Giants are orange, Mariners, Rockies, Twins, all those are their uniforms are that color. Some of them are not representative, Angels are not orange, but Angels are in Orange County, so okay, if they made those orange. Texas, I don't know what's going on with those teams, they're all just green. So representative colors here. Normally I would say don't have that many blues on a map, but because at least baseball people can distinguish between those different colors of blue, that's okay. Representative colors should be intuitive. So if we go down here, I'll come back up, don't worry. Annual precipitation. Dark blue means more rain. Light blue means less rain. And you look at this square here and you can intuitively figure that out. Annual average temperature. Dark red means hotter. Dark blue means colder. In between means in between that. And your brain looks at that and can figure it out automatically. Even altitude, which is kind of cool, your brain usually figures that out, where green means low altitude, white means high altitude, brownish is mountain areas. So those are intuitive things, which is representative colors. These are representative symbols, where some are hard to figure out, but you can figure out the streams. The water's blue, woodlands are green, things planted in rows is a farm. This map is an example of randomly assigned colors that kind of look like representative colors. So the oceans here, I took this from a Reddit post where somebody saw this in a textbook, so not my map, I didn't make it. But it's in a history book, and they made the oceans green. Your brain looks at green on a map and tells you that's land. Many of the countries are blue. Your brain looks at blue on a map and says, hey, that's water. So like we've got all this, the colors are opposite of what they should be, really. And it's like if I was making a purposefully confusing map, I guess I'd try to do that. Now, randomly assigned colors, these colors here in this World War I map are randomly assigned. Like the colors don't mean anything as far as I know. Randomly assigned colors are good for people things or maps where you know a color doesn't necessarily represent the stuff. Or like in the World War I map, you could maybe make countries the color of their flags. But like everybody's red and blue and white in Europe, so that's not going to work. For ethnic groups in the Levant, we have randomly assigned colors for ethnic group. They didn't say like, oh, Turkish people really like purple. No, not the case. Or as far as I know, not the case. Those are just randomly assigned colors to show ethnic groups in the Eastern Mediterranean. The way that randomly assigned colors work is the GIS randomly assigns them for you, and it will do its best to make those colors not touch each other. And so with just 5 colors, you can cover the whole world and have none of the colors touch each other, which is cool. Same thing works for states. If you have 5 colors in the United States, then the computer will randomly generate those, and they won't touch each other, so everything is clear. This is mostly representative symbols. And then we'll come back to the difference between representative and randomly assigned colors as we go on. Should be clear, though, these ones are representative, these ones are random. Though, I'll say this, anytime you have green on a map, make sure that green cannot be accidentally confused for forest or land. And anytime you have blue on a map, make sure that blue can't accidentally be confused for water. So on our Levant map here, this is water. And it's, I think, pretty clearly water. But, you know, here, that's not water. That's Italy. Here we have 2 different shades of blue. Ocean is one blue. Countries are a different blue. That's important to distinguish your blues. Be intentional about it. The color for buildings is not gray. Like if they use on the USGS map gray for buildings, that might be confused for rocks. Pink is a kind of unnatural color, except for like, you know, flowers. So that works well as a thing that kind of sticks out from the landscape like human development does. Now, with qualitative data, we're good. We've got that, either randomly or representative colors or symbols. For quantitative data is amounts, ranks, qualities of things. In a non-GIS context, quantitative data is something that you might put into an Excel or SPSS document. Quantitative data is usually easy to graph. It's usually easier to run statistics on. And so if you can do any of those things, that's a good indicator that you have quantitative data. If you have data that's like, this is hard to graph, I can't put it in an Excel document easily, then you might be looking at qualitative data instead. Quantitative data is broken down into a few subgroups. Ordinal is non-numeric ranked groups, like small, medium, large, grande, venti, the other one, I don't go to Starbucks, anything that's non-ranked. So this might be like low density, medium density, high density, freeway, surface street, dirt road might be ordinal. So that's quantitative, non-numeric data. Something is more, something is less. Numeric data has numbers, 2 subtypes of numeric data. Ratio is numeric data with a meaningful 0. So when you have 0 as a value, it means that the thing you're studying does not exist. Rainfall is a good example of that. If you look at a rainfall map and rainfall is 0 for a location, that means there was no rain that fell out of the sky. Population, if population is 0 for a place, then that means there's no people. Veg density, you could have no plants, you could have lots of plants. Speed, 0 means there's 0 speed, it's an absence of movement. Kelvin temperature, 0 means there's no thermal energy, there's no heat at all. Relative humidity, 0% RH means there's no moisture in the air. Interval data has a measured scale. It's numeric also, but the 0 is not meaningful. So elevation is a good example. You can have 0-foot elevation. That doesn't necessarily mean there's no land. It means the land is at sea level. And so like 0 is our sea level, or the water level. And yeah, sometimes that could be underwater. But on elevation, you can have negative values as well. And so if you're at -1, then you're 1 foot below sea level. Or if you're at -283, then you're in Death Valley at Badwater Basin. But 0 doesn't mean an absence of land, even though that land may be underwater. Temperature, degrees Celsius. 0 degrees Celsius doesn't mean there's no heat. It means water freezes. 0 degrees Fahrenheit means nothing. I don't know, maybe. But it doesn't mean that there's no temperature either. So ratio, interval, meaningful 0, non-meaningful 0. Now quantitative data is most commonly displayed with either graduated color, graduated symbol, or dot density. Graduated color and symbol kind of work the same way. You have a color or symbol that increases in size or intensity to represent changes in value. With color, you can have one color that goes from dark to light or light to dark, increases in intensity. You can have two colors that range, so dark blue to light blue to yellow to light red to dark red. And you can have multiple colors. These are usually your elevation ones. But graduated color, one or two colors typically that change in intensity to show change in value. We can use graduated colors in both raster and vector data. You can use this in polygons. You can use it in points and lines, but with point and line data, you want to be careful that you make point and line data big enough so you can see the differences in color. So like make sure your dots for cities or whatever have some size to them so you can see the color changes. But definitely great thing to use with polygons and rasters. Sometimes graduated color is also called choropleth. There's no L there for a couple years. I think my first GIS teacher called it chloropleth. It's not choropleth, it's choropleth. Or if you don't want to worry about it, just say graduated color. Here's some graduated color raster examples. We talked about our red to blue annual average. NDVI is normalized difference vegetation index. Light green, less plants. Dark green, more plants. Annual temperature range. So these first two were good examples of representative colors. Dark green, yeah, you could intuit that dark green is more plants and that light green is less plants. You can intuit that dark red, hotter, dark blue, colder. Annual temperature range, this is graduated color, but it is not representative colors. Temperature range is the difference between the hottest month and the coldest month. Here, purple means a small annual temperature range, so a small difference between summer and winter temperatures. Dark green is a large annual temperature range, a big difference between summer and winter temperatures. So our Mojave Desert, Death Valley, it's real hot in the summer and pretty cold in the winter. The coast of California kind of doesn't change more than 10 degrees throughout the year, where Death Valley easily goes through like 60 degree plus temperature changes. So this one, graduated colors, but not represented because purple doesn't. You don't look at purple and think, oh yeah, small annual temperature range. Green, definitely big annual temperature range. That's not a thing. And if I had made this map with like red is big temperature range, blue is small temperature range, that would have been confusing for people because again, you'd think, oh, red means hot, blue means cold, which is not the case. The green areas are hot in the summer, but cold during the winter. The purple areas are medium year-round. Yeah, they can be coldish, but it's California cold. It's 60 to 80 is average. Others, you get the idea. Dark blue, little lots of rain. Light blue, little rain. Now, one of the important things with polygons is normalizing your data. If you're showing population over a space, population over area, we normalize our data, which means to divide your value by the size of the place. If you don't do this, you get this issue that's very common where big places just have big values. So like if you have population of the United States, yeah, of course California is going to have more people. It's bigger. There's more room for people. Texas usually shows up as maybe 2 or 3 on there because, yeah, Texas is bigger, more room. New York, same idea. If we normalize that data, so we divide population by miles or kilometers, then we get persons per square mile or persons per square kilometer. Then it accounts for the difference in size. And yeah, California is still going to show up as the first or second most populated. I don't remember. Doesn't matter. But it's not going to be because it's biggest. It's because we have a lot of people living in cities. Normalizing that data will make Texas drop in population. Because, yeah, there's a lot of people, but it's also a very big place. Should you normalize rainfall? No. Rainfall is not measured as like cumulative land coverage. It's measured in, if you put out a bucket, how many inches fall in that bucket. Surface water, yes, that is an accumulation of area. So surface water is dependent on the size of the place. Median age, no. Average age of people is not impacted by the size of the administrative district they live in. Number of plants, yes. If you have a big area, there's probably going to be more plants. If you have a small area, probably going to be fewer plants. Normalize it. Population, yes, normalize it. The next way to symbolize quantitative data is with graduated symbols. This is similar to graduated colors, but we have a symbol that increases in size. In ArcGIS, they like to give you a symbol with an outline on it as the default, and it really bugs me. I always try to make sure that I go into the symbol choices and remove that outline. If your dots are too small, it makes it really hard to see the colors, and to me it's distracting and looks bad. So I always try to remove the outlines of my symbols, or at least make them gray or transparent or less intrusive. Again, graduate symbol, one symbol, increases in size, shows your change in value. This is a US Census.gov automatically generated map. It's got graduate symbol, big dot, more people, small dot, less people. This map of Texas has both graduate symbol and graduate color. Small dot, small city, bigger dot, big city. Light gray, less populated county, dark gray, more populated county. Graduated colors, graduated symbols. Cool. Dot density, of the 3, this is my least used one. Maybe you'll find that you really like dot density, but it's just not for me. One of the problems with it is that it randomly distributes the points over your study area. So if you have a big study area like states at the national scale, then look at the population of California. We all know our population is not randomly distributed across the state, nor is any of the states. Our population is concentrated in cities, usually. The way to get around that is to reduce the size of your administrative boundaries. So at this scale, instead of using states, use counties. And so now we can see, okay, we have more populated counties, less populated counties. Here, the county borders kind of get in the way, make it hard to read the map. So what I like to do, here's a kind of a second trick, or first trick, here's the second trick. Make your county borders transparent, or get rid of them. Not white, because then they'll show up under your dot still. Just make them transparent. And you get the confinement of your counties without the intrusive lines. And so this, in my opinion, looks the best. Now, this isn't perfect because we know that like LA County population is not randomly distributed across LA. There's nobody in the San Gabriel Mountains, less people in Lancaster. You get the idea. But this is better than that. With this, you can set the dot size value. So here, 1 dot equals 100,000 people. You could make this a more empty map by making 1 dot equals 1,000,000 people. You could make this a much busier map by saying 1 dot equals 100 people. You could go wild and say 1 dot equals 1 person. That may crash your computer, because now your computer is going to try to draw 400 million dots. So maybe don't do that, depending. One of the benefits of dot density is you can use this to kind of artificially randomize your data. So if you have a sensitive population, if you have animals you're trying to not show exactly where they are, or people that you don't want to show exactly where they are, you can use dot density to randomize your locations without changing your data too much. Just be careful about your administrative district size. Now, coming back to data, classification of data is the way that we break data into groups. In GIS, the default method, and in my opinion the best one, is natural breaks. This lets the computer look at your data, and it breaks it into naturally occurring groups based on what's best. So look at this data set right here, this row of numbers. In just a minute, pause the video and try to break this into 4 or 5 groups. See how it goes. Okay, pause. All right, you unpaused. Usually I break this into groups like 1 to 5, maybe 8 to 10, 12 to 15, 16 to 20, 20 to 25. Maybe you chose to break it up differently. And so what we did right now, that's technically manual. That's doing it yourself. But our manual version was similar to what natural breaks probably does. Usually it looks good. Usually it gives you the best distribution based on your data, so that's nice. Kind of a trick that I'll do for maps that I want to look good. I'll do natural breaks, and then it gives you these wonky categories here. The nice thing about manual is you get these nice round numbers for your categories, and so I will do natural breaks and then round these off myself. So the top one, I'd say, if that's 629, I'd say, okay, let's just make that less than 600. This one, less than 2,000. Here, 6,000, 20,000, maybe 68,000. You get the idea. And that usually looks better, or looks best. Quantile and equal interval are things that you'd use more often in other disciplines. Probably the most common way that you experience equal interval is in grade distribution. When faculty assign grades, if you got a 90 and up, that's an A, 80 to 89 is a B, 70 to 79 is a C, and so on. With population doesn't follow those nice equal distributions most of the time, and so equal interval, I think I forgot to define it. Classes with an equal range does not account for the values that fall into each range. It's just the range is the same size. So here, all of the states fall into the same lowest category, and then Washington, D.C. is really dense compared to everything else. So it's got its own category, and there's nothing in between. So equal interval, not appropriate in this case. We don't have a very useful map. Quantile, also good in a lot of cases. Quantile makes nice looking maps. It breaks your data up into categories with the same values, same number of features in each range. And so if we have 50 states in 5 categories, then you're going to have 10 states in each group. If I have a group of students, let's say 25 students, and I need to assign grades, okay, 5 people get an A, 5 people get a B, 5 people get a C, and so on. Probably not very fair, but if you mapped it, oh, it looks pretty. Look, we have the same number of each color. So this may not best represent the population because now we grouped Washington, D.C. into some county with 142 people in it, or per square mile. So we have a very populated place grouped with a unpopulated place, and that does not work well. I'd say that's not a good thing to do, but our map looks nice. So sometimes quantile is good. So in this case, bad. Sometimes equal interval is good. In this case, bad. Which is why natural breaks is good because it tells you the empty places, and it tells you, in this case, the populated places. All right. That's good for data, cartography, data classification, and symbology. Have a great day.